Hello everyone, welcome back to the latest lecture session. Let's look at the bigger picture, what we are trying to do and what we have done so far so that we can understand what we need to do. We are looking at providing potable drinking water. We are not talking about water that's remarkably contaminated by a specific contaminant and such, because if that is the case, there are a number of contaminants that can contaminate the water. We are talking about general water, let's say surface water body, lake, right? So in that case, how do we go about it or such, let's say, right? So we were looking at removal of turbidity, the suspended particles, as being one of the major issues. So we looked at combination of coagulation, flocculation to make the particles bigger, come together and then bigger, and then removal by sedimentation. Then the relatively smaller particles which are still suspended, or some of the bacteria which won't settle down or which haven't settled down. So you look at filtration. Filtration, we looked at two aspects: depth filtration and membrane filtration. So we removed most of the suspended particles. And if the water is groundwater and has high hardness or such, well, we'll look at that relatively later. Hardness meaning calcium and magnesium, relevant issues. They are dissolved ions, but we will look at that aspect later. So what else do we need to look at? I removed most of the suspended matter which will cause relevant issues or harbor, provide sites for pathogens or bacteria. So I need to remove that. Other than that, general issues with suspended matter too. So by now, or by looking at the process so far, we have removed the turbidity or the suspended matter. What else? What else? We are going to look at the primary aspect when we supply drinking water. We are talking about seeing to it that the population doesn't fall sick due to bacteria or harmful bacteria or pathogens, right? So now we are going to look at the last step in a traditional drinking water treatment plant, which is disinfection, right? So disinfection. We already looked at why we need it. This was in the context of wastewater treatment, so I'll not go into great detail in this particular session, but I will skim through it. And some of the slides we are going to reuse them because they are applicable here too, right? So disinfection. Firstly, why? We'll cover that. Pathogens, this is causing, especially in water, we need to be relatively, drinking water, we need to be especially stringent. And we looked at some of the methods there, so a quick recap. Firstly, when I talk about methods, what is the principle here? Here we are going to have cells, right? Either bacteria cells or, with respect to viruses, RNA or DNA. I need to damage them or see to it that they become inactive such that they can't replicate, right? So typically they replicate pretty fast. I think we saw this via one example in wastewater treatment, right? So here I want to see to it that either I damage them or such that primary aspect is I want to make them inactive or see to it that they don't replicate. So different ways. One is by adding a strong oxidizing agent such that the cell wall, let's say of bacteria at least, can be damaged. Cell wall, organic matter, oxidizing agent, right? Electron acceptor. So it will go and oxidize this relevant cell wall. So then cell, constituents or such will come out and you are going to have relevant damage. So we look at a class of oxidizing agents or a group of oxidizing agents as disinfectants. Again, based on the relevant dose, relevant time, we are going to have different kinds of effectiveness for certain kinds of disinfecting agents, different effectiveness for different disinfecting agents or oxidizing agents. And another category is UV. It is UV irradiation, ultraviolet irradiation, and we looked at germicidal action based on irradiating water with 253.7 nanometers. So that's something we are going to cover today, right? So let's see. Goal, we know that we want to kill, I guess kill is the layman's terms, right? Inactivate pathogens or sometimes kill them too, obviously, right? While minimizing the formation of harmful products. When I say harmful products, this is disinfection byproducts, which is of great relevance in the Indian context. Let me move on. So in India, for drinking water, what is the relevant standard? You know, I think we also looked at this earlier when we were talking about water treatment. So what is it we want? We want zero total coliform count. So they want zero, let's say, in any 100 ml sample. Well, keep in mind that it's not as if I take sample every day and such. Typically when I suspect it, then I take it. There is supposed to be a regular testing, but in India with the infrastructure that we have and based on our needs, we still are lacking in that aspect. We are obviously increasing. But what do we have? We have zero total coliform. Let's compare that with US EPA, right? So it is fine with 5% positive total coliform, right? That seems a bit surprising, but the rider here is that you have to take more than 40 samples per month, especially when the population is greater than 33,000. Again, there are more details which we are not going into, but here it is specified about the number of samples per time and what is the acceptable positive here, let's say, right. So that's something to keep in mind. Disinfection methods, typical oxidizing agents based on chlorine typically, and then ozone, O3. Reason for liking this or preferring this is it will increase the final oxygen in your water. Other than that, it will also not increase to any dissolved solids. All this, it will at least add to Cl minus, right, and increase the TDS. That's something you don't want to have in your system over time, adding more and more dissolved solids, right. After, what do we say, oxidation and your oxidizing agent being reduced to Cl minus, you are going to have Cl minus, which is very much going to be dissolved in your solution, right. That's why I am saying it's going to increase the TDS. But with O3, we are going to have oxygen as the final product, and oxygen, obviously it's not going to lead to TDS issues. We want higher oxygen content in general. And then UV, right, and the radiation or the wavelength was 253.7 nanometers, let's say. Yes, let's move on. What are we concerned with? To test the unit at specified flow and velocity with test organism, right. And I guess we covered these aspects and ensured that the doses measured in the test are adequate for desired removals. So that's what it comes down to, right. So again, these aspects we covered, so I'm going to skip this. And we looked at different laws, and the first law we looked at was only considering the concentration of the microbes and saying that the rate is going to be dependent upon the concentration of the microbes, Chick's law. But obviously we know, or in general people know, that the concentration of your oxidizing agent or the disinfecting agent is also important. So that's why you are going to have the Chick-Watson's law, which also takes into account the concentration of the relevant disinfecting agent. So here Chick-Watson's law, it takes both the microorganism concentration and also the concentration of the relevant disinfecting agent into account, and we discussed this. And we also looked at plug flow, why that is better and how to come up with this equation. Typically plug flow is what we look for, and we looked at the actual pictures of some of the disinfecting systems and such. Primary variable, obviously concentration of disinfectant is one aspect. It should not be too high. Why is that? Because then it's going to react with NOM and form these harmful disinfection byproducts, which we are going to discuss later. And disinfectant itself might be toxic at high concentrations. It can lead to odor and taste. This you would have seen in India, especially sometimes when people add high chlorine at the treatment plant, right. So retention time, obviously we know that how much time the disinfecting agent is in contact with your particular pathogen or the water will certainly play a role. So that is why we also look at theta, not theta, yeah, hydraulic retention time theta. So the product of C theta determines the effectiveness of the disinfection, right. So that's called the dose approach, C theta. So plug flow, why? In general we saw that if it is CSTR, assuming that it's completely mixed, right. So whatever comes in, if it's immediately being mixed, right, this is my water with relatively high, not high, at least reasonably high pathogens coming in, and this is my effluent. So here at least Indian standards, what is it, or any standard typically pretty low, it's 0, right. We know that the effluent has to be 0, but if something comes in and is completely mixed, what is it? It can't really be 0. So that's why you are obviously going to move away from, what do we say, the CSTR kind of systems and try to go for or achieve plug flow systems, right. So typically long and narrow tanks or baffled tanks, this is something that we discussed. So two aspects to consider. One is primary, obvious aspect which we discussed until now, we want to inactivate the relevant pathogens. Secondary, to maintain disinfectant residual. Why? So that you will have some oxidizing or disinfection capacity in your distribution network, so that if there is any microbial growth, it can be taken care of it, or if there is any pathogen entry into the distribution network, then also this residual disinfection or disinfectant residual can take care of that particular aspect. So, what is the step by which, or what is the mechanism by which chlorination gets this disinfection done? It is by oxidizing the cell wall of the microbes typically, and it can be applied in various forms as chlorine gas itself or OCl minus and such, right. So, we discuss this again. Chlorine gas, again, once it's dissolved in water, it will again form HOCl. HOCl is an acid, and obviously, as we know, it will stay in equilibrium with the deprotonated form, which is OCl minus. But in general, we know HOCl is about 80 to 90 times more powerful oxidizing and disinfecting agent than OCl minus. So, typically, you need to look at the pH and pKa to see to it that you have relatively reasonable HOCl without the pH dropping low. That is something to keep in mind. So, hypochlorite, if I add this, again, as you can see, after you dissolve, you are adding OCl minus, and NaOCl2, I guess Na plus and OCl minus. OCl minus, we know, will again be in equilibrium with HOCl, right. So, in effect, we are trying to add the oxidizing agent HOCl, right. That is what we are trying to do. Chlorine demand, let us say, what is the dose equal to the demand plus the residual, right. This will be the aspect, the dose. So, free chlorine, we are going to mention that as HOCl or OCl minus. Combined chlorine, if it is combined with NH2 or NH, we are saying that or referring to that as combined chlorine, right. And chloramines, right. I guess combined chlorine, chloramines, typically they are long, last long, but again their disinfection lethality is relatively low. Chloramines also contribute to chlorine residual with residual free chlorine, as I mentioned, because they are longer lasting. For residual chlorination, this is relatively decent. And one aspect we mentioned was, or we discussed earlier, which I am not going to go into great detail now, is the chlorination breakthrough curve. What is this about? So, in water, it is not just the pathogens that are there, there are many compounds that can be oxidized by your oxidizing agent, and your oxidizing agent is not specific. It is not going to go and disinfect what you want, it is going to oxidize whatever it can come in contact with, right. So, you have to take care of all these other, what can I say, scavengers. So, if you have Fe2 plus or H2S, which are reduced compounds, they will be oxidized by your chlorine, so they will take up some of the chlorine. That is what we have out here. And after that, we were going to have formation of these chloramines, let us say, right. Depending on the concentration of chlorine, you know, you are going to have different ratios, and that is what you have. But after a certain peak or after certain concentration of chlorine has been added, what is going to happen? You are going to have destruction of these chloramines, let us say. The final one that is going to be formed is going to be unstable. So, you are not going to have any chlorine left after a certain point, let us say, right. That is going to decrease. That is why you see that the chlorine residual is decreasing, right, and this is the break point, let us say. And after that, whatever you add will stay as free chlorine, right. So, that is something to keep in mind, free residual and combined residual, I guess, right. So, that is something to keep in mind. Why is this increasing? Again, I discussed this well enough in the wastewater relevant aspect. Here we are having the chloramines being formed, and after a certain point, due to stoichiometry and relevant aspects, the chloramines will be forming another kind of compound which is going to be unstable, let us say. So, that is why it decreases. Again, in that context, we saw this, let us say, right, ammonia. Again, for this, obviously it depends on NH4 plus present, right, reaction of Cl2 with the ammonia. That is why NH4 plus is decreasing. And here we have, what do we say, all the types of chloramines. So, typically that is constant, and then the unstable compound formed, and that is why it decreases. So, chlorination breakthrough steps, let us say, right. So, we mentioned this already, whatever reduced compounds are there, not nitrate though, H2S and Fe2 plus, nitrate is already oxidized compound. Chloramines are formed creating combined residuals, right. So, maybe NH4 plus is a better option. Low point is break point, and after that whatever I add will stay as the free residual. That is something to keep in mind. So, depending on your relevant limits, you have to add that. So, chlorination breakthrough, we are done with that. What is the concentration that I have to add? Obviously depends on the type of water sample. From one place to the other, it is going to vary. and typically we want 0.2 at the furthest point. For example, in IIT Roorkee, it was built up over time. Sometimes, things pass by, and there are certain sections where water or the distribution network is at a dead end. So the water spends a lot of time in that particular section. No fresh water comes through unless it's used vigorously in that particular house or at that particular, along the houses in that road, let's say, right? So here, the residual chlorine might be pretty less. So you have to be aware of these kinds of aspects. So at least that's something I wanted to mention, let's say, dead zones and such. So, but it's objectionable, as in the chlorine residual, if it's higher than 0.5 milligram per liter, it becomes objectionable. Then disinfection byproducts. So you can never have too good an aspect of anything, right? Too much of anything is bad. So that's what you have. If you add too much disinfecting agent and you also add or have organic matter, you will have what are called as disinfection byproducts. So formation, we discussed this aspect. More importantly, organic matter. Typically, people call it as natural organic matter, but in India, the organic matter could also be due to human causes, let's see. And then free chlorine, you have relevant organic and Cl compounds being formed. Typical NOM structure, you see this aromatic structure, right? And again, remarkably complex too, yes. And so with that, you are going to have the relevant DBPs being formed. Again, we looked at this pathway earlier, so I am not going to great detail here. Oxidation and substitution are the relevant primary steps, right? Incorporation of chlorine to organics, and then finally you will have this like chloroform being formed. And as I mentioned this, I mentioned in the case of wastewater, but I should have mentioned this in the case of water. Why do I say so? I guess I should give the background here and spend some time. So here I have Mathura, here I have Agra. And we have, I think, 150 MLD treatment plants here, okay. And what's the issue here? Downstream of Delhi, due to various reasons, historical, explosive growth, infrastructure not being able to cope up with the relevant population influx, and also in the kind of technology being used, and more importantly, people also not contributing to laying the distribution and sewerage network. We have, Yamuna being relatively polluted. So this water being taken up at Mathura, it has high organic content, 6 to 14 DOC, dissolved organic concentration. BOD is, I think, around 30, and COD will be relatively higher, let's say. And the fecal coliform or total coliform will be in lakhs, and so, if I am not wrong. So it's pretty high. So what's happening? The traditional one, as in based on the steps we discussed until now, coagulation, flocculation, sedimentation, filtration, and then disinfection, it leads to considerable THMs or trihalomethanes or disinfection byproducts being formed. But I was told that mostly the people use it for, not for drinking, but for other purposes and such. For drinking, they have other sources. But one aspect is THMs, the primary route via which it affects us is not just drinking water. So when I take a hot water shower, relatively high, skin is also relatively warm, so it can permeate through my skin and affect my body. But again, in India, there are a lot of other issues to be concerned about. So as of now, THMs and DBPs are not at a great priority. But soon as our standards improve, I am sure that these aspects will come into the picture. But again, I am only mentioning a couple of plants. There are obviously many other plants, and one has to measure them, right? So in Agra, though, they were not using a traditional one, they were using a MBBR, moving bed biofilm reactor. That was doing a very good job with respect to removal of BOD and COD. But even there, I saw that the DOC was pretty high and the DBP concentrations were still remarkably high as compared to, or as much high as the one in Mathura, where they had the traditional treatment plant. So that's something to keep in mind. And the chlorine doses that they were having at Mathura that was required was pre-chlorination. They were chlorinating it at almost 100 milligram per liter. Think of that, pre-chlorination anyway, initial chlorination, so that they won't have microbial growth in their relevant sedimentation tank and such, 100 milligram per liter. So you can understand the doses that they are having. So types of DBPs, The ones that are regulated in India are the trihalomethanes, methane, CH4. So when you have trihalo, I guess, right? Let's just look at it. So halo, 3 halogens. Same case, 3 halogens. Yes. Again, 3 halogens, let's say. I guess this should have been Br2, dibromo, right? So 3 halogens, right? Trihalomethanes. So this is one thing. And in India, we have the standards for this. Yes, this is from BIS as mentioned here. But in this case, one aspect to consider is I am just comparing the standards of the relevant DBPs as given in various countries. So what did we adopt? We adopted whatever WHO is suggesting. As you can see, that's the highest that people are following, 40 ppb. And US EPA, what is it, like 50, 75 or something? EU much lower, yes, and Canada too pretty low, Australia too. So you see that, you know, we do have standards, but our standards are typically relatively more lax. But again, we are a developing country, there are many priorities. So that's one thing. As technology comes in, people can afford it, and we have the capital for the relevant expenditure and such, we will have to look at it. But obviously one aspect is to have citizens and students who are more technically competent and obviously aware. So that's the job we are trying to do here, right? And another set of DBPs which is typically regulated but is not regulated in India are the haloacetic acids, let's say, right? Again, monochloroacetic, dichloro, trichloro, monobromo and so on, but in India they are not regulated. In the US and other countries they are though, and as you can see it's pretty low, 60 ppb or 0.06 milligram per liter. So chloramines and combined chlorine, let's come to that. Again, I discussed this earlier. So if required, add ammonia with chlorine to intentionally form combined chlorine, let's say, right? Anyway, this we discussed. So how do I do that? I can do this, right? Monochloramine, I guess. We will typically add these as the relevant, what is it? Oxidizing or disinfecting agents, let's say, right? Okay, here we have that. But we also mentioned this aspect. This is the one that is unstable. So I'll come back to that breakthrough curve. So if I increase the chlorine concentration or HOCl concentration beyond a certain point, it's going to start reacting with NHCl2 and form NCl2, which is remarkably unstable, and it's going to destroy the combined chlorine. That's something to keep in mind. So the concentration at which you are going to maintain it is important, let's say, right? So as I mentioned, it's weaker, pretty weaker, particularly for viruses. We discussed this earlier, but one advantage is it does not form the trihalomethanes. But it is unstable, really not really, it spends more time. This is an aspect, I guess. So combined chlorine residual often added before distribution, okay. So looks like this is unstable, it will not provide long lasting residual. So combined chlorine residual again has to be often added before distribution, right? Or a different type of chlorine has to be added here. That's something to keep in mind when looking at these chloramines. Ozone disinfection, right? We mentioned this. One advantage is does not form trihalomethanes or haloacetic acids, but forms something else which is harmful. It converts bromide if it is present in water, if bromide is present in water. It is not the issue of ozone reacting with organic content though. Ozone reacting with Br minus. So if Br minus is present, we need to be concerned about bromate. But in India, we don't have any standard for this. But again, this is toxic compound, if not carcinogenic. We can check that. But US EPA does regulate that, and as you see, it regulates it at 10 ppb, which is pretty low. So ozonation, one of the strongest oxidizing agents out there, probably the second strongest. So this is the relevant half reaction, very strong electron acceptor, right? So the next kind of disinfection is not based on oxidizing agent, but ultraviolet irradiation. And low pressure lamps, monochromatic, they emit radiation at 254 nanometers, and this particular wavelength is absorbed by the RNA or DNA of viruses, and you are going to have, what do we say, inactivation of these viruses. The process or the mechanism we explained earlier when we are talking about wastewater treatment. And though we say that it can also form hydroxyl radicals, it forms hydroxyl radicals when you have 185 nanometer wavelength, but this is rarely used. but it will also, UV can also lead to formation of hydroxyl radicals, the strongest oxidizing agent known probably, when we add hydrogen peroxide. But again, that's a different aspect, but I wanted to mention that. Let's see. Why am I mentioning this? If you want to remove any of the persistent organic pollutants, then you will have to add this hydrogen peroxide, which will lead to formation of this very strong oxidizing agent, which can degrade these persistent organics, but that's a different aspect. But I want to mention that typically we look at low pressure and 254 nanometers, right? So as you can see here, we have bacteria, right, and virus and such. Here we have different disinfectants and what do we say, a comparison here. We already looked at this earlier, but one aspect to keep in mind is the relevant lethality. For example, look at ozone, right? Again, this is 1 log 99.99%, 99.9% removal and so on and so forth. Let's say for protozoa and cryptosporidium, again, right, that's of considerable issue in India, let's say Giardia lamblia. You see that, you know, it's relatively what do we say, lethal, ozone or even UV, right? But with chloramine, one of the weakest, you see remarkably high doses which are almost impossible to add, let's say. So the choice of your disinfecting agent should certainly depend upon what it is that you are trying to achieve. So if you are concerned with protozoa, then I guess chlorine or chloramine certainly are not maybe a great way to go about it, right? So again, with viruses and such, you see that chlorine does a decent job, yes, and even for bacteria it does a decent job. But with respect to protozoa, which again are pretty prevalent in Indian context, I guess chlorine, as you can see, doesn't do a great job with respect to cryptosporidium. So control of DBPs. After forming the trihalomethanes or haloestic acids, it's difficult to remove them. Typically you can have what do we say, organic what do we say, compound or hydrophobic compound adsorption onto GAC and such, but again that's like, you know, creating a problem and then trying to solve it. So typically this is not done. Generally what do we do? Again, air stripping, GAC, right, again addition of more disinfectant or again cost, so that's not something that's usually done. What do? We remove the cause or one of the building blocks for formation of DBPs. We know that Cl2 or the disinfecting agent and NOM or organic matter will lead to formation of DBPs. So rather than trying to tackle this, people try to tackle this and remove this, right? So that's what we do, remove the precursor, let's say, right? And here there are different ways. One is enhanced coagulation or enhanced softening, which will remove some TOC, right? So that's one thing to keep in mind. Again, different stage 1 rules and such in developed countries, especially the US, they are going to implement more stringent conditions with respect to NOM. Rather, they already implemented it and they talk about DOC being relatively less than, I think, 2 or 1.5 milligram per liter, which is not the case in India. But in India, I think this should be adopted because of 2 reasons. One reason is obviously if it's high, then the DBP concentration will be high. And secondly, and this I feel is pretty important, in India now we have these persistent organic, trace organic compounds which are synthetic in nature. For example, I am taking a pharmaceutical compound, only 20% is used, 80% goes through. Well, depends obviously, I am just giving an example, and that's not good for either the aquatic ecosystem or even if it goes to the food particle and enters the food chain and enters my system, it's not good for me either. So for removing them, you know, typically DOC is a better parameter, but I guess we are yet to catch up in that aspect. Again, depending on the alkalinity, your TOC removal also will be dependent, but just some thumb rules out here, let's say, right? If the source water is this and relevant alkalinity, what is the TOC percentage removal you will expect, right? And again, some will be removed when we are looking at addition of what do we say, the relevant precipitate or formation of the relevant precipitate, because organic carbon or TOC will be adsorbed, right, adsorbed onto this solid. Yes, that's something to keep in mind. This is AD, adsorbed, right? Or you can use membrane filtration rather than sand media filtration, but one issue with membrane filtration, which we already discussed earlier, I guess, was if we have high NOM, it will lead to fouling considerably. So that's one aspect, and that's why, as I mentioned, I like ozonation, but in India yet to come up in great, what do we say, find great acceptance. But with NOM, you are going to degrade this, or ozone will degrade the NOM. So that's one reason why I like usage of ozone, right? So you can modify the type of disinfection, right? Change the dose, but not a great idea. Change the location of application. Yes. And concern for pathogen removal, particularly cryptosporidium, is causing more use of ozone or combined chlorine. But again, typically ozone, that's what I mentioned, cryptosporidium protozoa in Indian context, right? So with that, I'm done with disinfection, and we are done with the traditional ways or traditional water treatment plant when trying to treat surface waters. But what else is coming up, or what else are people trying to do? Because now the challenges are not what we faced earlier. So we have multiple other challenges. So again, technology tries to catch up to these challenges. And so these are aspects we will look at in coming from the next session. But before we go into the more, what do we say, or relatively recent advances, or not very recent though, right? They have been in vogue since 1 decade or 2, if not. We will look at lime soda softening, especially relevant when we are talking about hard groundwater, let's say. So with that, I'll end today's session. Thank you.